Hi, in this video we will discuss bias variance trade-off. So let's say we have different samples from our population D and we train different estimators F1, F2, F3, Fn on different samples of the population D1, D2, D3, Dn. So the bias is defined as mu minus Fx, where mu is average of or you can say expected value of Fx. So basically mu is the expected value, that what would be the value of Fx you will get from the estimator or predictor if you train that predictor on different datasets. So bias tells us that on an average how much deviation would our predicted answer show from the actual answer. So what's the difference between the predicted answer, average predicted answer, and the actual answer? So that's called as bias. So if you take a very simple model which is like kind of underfitting and not able to fit properly to the training dataset, then you will have high bias. On the other hand, variance means that what is the variance of these predicted values when we train the model using different datasets. So variance is nothing but Fix minus mu whole square divided by n sigma I is equal to 1 to n. So this is variance of estimator f dash. In other words, this is just the expected value of, so mu is simply the expected value of f dash x, and we have to take the expected value of f dash x minus expected value of f dash x square. So this is the variance for f dash. Now let's see how we can split the average squared error in terms of bias and variance. So the average squared error, or we can say expected value of square error, is the expected error we can get from our predicted model if we train our predicted model on different datasets, different samples of the complete dataset. So the average squared error for in any given point x can be written as expected value of f dash minus f whole square, where f dash is the predicted value and fx is the actual value, which is a constant given x. So which is nothing but, we can write this in the form of f dash minus mu plus mu minus f whole square, where mu is nothing but expected value of f dash, as we just saw. And we know that this would be equal to f dash minus mu whole square plus mu minus f whole square plus 2 times f dash minus mu into mu minus f. So for given x, fx is actually a constant, so, and mu is also a constant since it's expected value of a random variable, so mu minus f is a constant, and hence we can break this expectation into 3 terms, which is expectation of f dash minus mu whole square plus expectation of mu minus f whole square plus 2 times mu minus f. All the constant terms get out of the expectation and inside it remains f dash minus mu. Now since mu is expectation of f dash, so this term here becomes 0, and that's why this value would be equal to, now f dash minus mu, expected value of f dash minus mu whole square is nothing but variance of f dash, and we know that expected value of mu minus f whole square is nothing but mu minus f whole square, because mu and f are constant, they are not random variables. Given a particular x, mu and f are constant, and that's why we can take that out. And now we know that mu minus f is nothing but the definition for bias. So our expression becomes the average squared error or the expected squared error is nothing but variance in f dash plus bias in f dash square. So bias in f dash is basically expected value of f dash minus f of x. So the thing is, when we want to find an f dash, such that this error can be minimized. Expected value of f dash minus f square can be minimized, and we know that both the variance and bias are positive terms. Sorry, both the variance and bias square are positive terms. So we have a trade-off in the sense that if we take a too complex model or a model with too many parameters, or we can say a model which tends to overfit, so those models, if we use different data sets, those models have very different predicted regression lines, or we can say predicted boundary lines, and hence variance is quite high. On the other hand, if we use a very simple model, a too simple model with too less parameters, or a model which we can say which underfits, in that case the bias gets very high, because the difference between the mu, which is the average predicted value, and the f, which is the actual value, gets very high. So trade-off is that we want to choose a model such that both variance and bias are particularly low. Let's try to understand this further with the example.